All right, welcome. Today we're going to tackle a question that sounds super simple, right? But it's actually one of the most profound questions in all of physics. Seriously, it's the key to understanding everything from a simple bouncing ball all the way to the motion of the planets. So let's get into it and figure out how you really know if you're moving.
So let me ask you straight up, are you moving right now? I mean, you probably feel like you're just sitting still, right? In a chair watching this. But here's the thing, you're on a planet that's spinning at about 1,000 miles per hour. And that planet is whipping around the sun at something like 67,000 miles per hour. So what gives? What's the right answer? Well, it turns out it's not that simple at all. It all comes down to what we call your frame of reference.
You know, this exact problem was a real head-scratcher for thinkers for, centuries. It took the incredible mind of Galileo Galilei to finally crack it with this brilliant thought experiment. What he did was he imagined himself sealed inside the cabin of a ship, sailing on a perfectly calm sea, totally cut off from the outside world.
And what he figured out inside that imaginary ship? Whoa. It became a cornerstone of physics. He realized that the laws of nature, the rules of the universe, are the exact same in what are called inertial frames. Now I know, that sounds super technical, but trust me, it's not. An inertial frame is just a place that isn't accelerating. That's it. It's either standing still or it's moving at a steady, constant speed and a perfectly straight line. And Galileo's big insight was that in any of those situations, physics works the exact same way.
Okay, let's make this super relatable. Picture yourself on a bus. If the bus is just parked and you bounce a ball, it goes straight up and down, right? Easy. But here's the cool part. Now imagine that bus is moving at a perfectly smooth 50 miles per hour. No bumps, no turns, just a constant speed. And you bounce that same ball. What happens? It still goes straight up and down, at least from your perspective on the bus. So if you couldn't look out the window, how would you even know you were moving? You wouldn't. You literally couldn't tell.
And that is where the secret is. The key, the whole shebang, is acceleration. The second that bus driver hits the gas or slams on the brakes, oh, you feel it. The ball goes flying, you get thrown forward, everything changes. But as long as that speed is constant, that state of perfect balance, that equilibrium, is completely identical to being at a dead stop. This is basically Newton's first law of motion. You know, an object in motion stays in motion, but it's applied to your whole world, your entire frame of reference.
Okay, so this whole idea was so powerful that physicists, of course, took it to the next level. They started thinking, okay, if the laws of physics are the same in any of these non-accelerating frames, what would the absolute perfect frame for an experiment look like? I mean, what would be the ultimate physics lab?
And that led them to create this perfect thought experiment, the idealized inertial frame. Just imagine a little box, floating out in the deepest part of space. It's completely free from gravity. No pushes, no pulls, nothing. It's a place where if you push something, it would just keep going, perfectly, forever.
Now, let's be real for a second. A place with absolutely zero external forces, it doesn't actually exist. But that's okay. That's not really the point. As a tool for thinking, as a concept, it's unbelievably useful. It gives physicists this perfectly clean slate, a baseline to measure all real-world motion against. It lets them figure out the fundamental rules without any pesky interference.
But that brings us to a really big question. It's one thing to imagine this perfect lab, this pure inertial frame, but can we actually find one? Is there anywhere in this gigantic universe of ours that's totally, completely free of any interference?
I mean, really think about it. If you could travel to the deepest, darkest, emptiest void between galaxies, could you find a spot where you are genuinely 100% still, with absolutely no forces acting on you at all?
The answer is almost. So close. It's tantalizingly close. But it turns out there's this one tiny little problem that messes everything up. And it's everywhere in the universe.
Yeah, it turns out the universe has a built-in complication. It's something called tidal forces. And no, we're not just talking about the ocean here. This is much bigger. It's the basic fact that gravity is everywhere. Every single thing with mass, every faraway star, every planet, heck, every tiny speck of dust out there is pulling on you, right now, with its own little bit of gravity. Think about it. You can never get far enough away to escape all of it. It's impossible. The pull from any one thing might be so small it's almost nothing, but when you add it all up, it's always there. It's like a constant cosmic background hum of gravity. And because of these tiny non-stop gravitational tugs coming from every direction, finding a 100% perfect, truly still inertial frame is, well, it's impossible.
So, if a perfect frame is totally impossible, then how does anything work? I mean, how can we do science or build a skyscraper if our basic reference point is always being jiggled around by the rest of the universe? Well, it turns out the solution, we're standing on it.
There's this fantastic phrase used to describe our planet in the material for this explainer. It calls Earth a stabilizing groundwork. It sounds great, but what does that actually mean for you and me?
Okay, so let's get this straight. Technically speaking, Earth is not a true inertial frame. Nope. Like we said, it's spinning, and it's orbiting, and those are both types of acceleration. But, and this is a huge but, for pretty much everything we do in our daily lives, and even for most scientific experiments, it is an incredibly good substitute. It's our lab frame.
So here's the magic behind it. First, you've got the Earth's constant motion, right? The spinning and the orbiting, all that acceleration. But you also have this second massive factor, Earth's own powerful gravity. It's so strong and so consistent that it basically overpowers everything else and pins us down. And the result? You get this incredibly stable, predictable environment where physics just works consistently, day in, day out.
And you know what? This is the big takeaway right here. This stability is everything. It's why engineers can build skyscrapers that don't fall over. It's why scientists can get the same results from an experiment today that they got yesterday. It even creates the kind of equilibrium that life needs to exist in the first place. Our planet is such an amazing, good enough inertial frame that for most of human history, we had no idea we were even moving. You actually need a really clever device, like a Foucault pendulum, which is just this huge, heavy pendulum that swings for a long time, to even see the proof that the Earth is slowly turning underneath it.
So think about where we started. We began with this simple little question, are you moving? And where did we end up? With the entire universe constantly pulling on us in tiny ways, and our own planet acting as this giant, stable spaceship carrying us through the cosmos. It really makes you wonder, doesn't it? If a rule this fundamental was basically hidden from us in plain sight for so long, what other incredible hidden rules are out there governing our journey through the universe, just waiting for us to find them?